Hi, welcome to Lesson 8.5, Solving Exponential Equations. The goal of today's lesson is to solve exponential equations in one variable using a variety of strategies. The reason for doing this is so that we can solve real-world problems involving exponentials. Okay, so let's take a look at this first example. We want to solve the equation 4 to the power x equals 8 to the power x plus 5. Well, there's a few ways of doing this. One way is to get a common base on both sides and then solve for the variable in the exponent. So let's take a look at that method. So 4 and 8, think about those. They will have a common base, or you could write them as powers of common bases. And that common base would be 2. So let's change 4 to 2 squared to the power x, and then 8 can be written as 2 cubed to the x plus 5. Then we can simplify the powers using power laws. So we get 2 to the 2x equals 2 to the 3x plus 15. Now, because the left side is equal to the right side, that means that the values are the same. And because both of the bases are the same, that means that the exponents must be equal. So we'll set the exponents equal to each other. And now we'll solve for x. Okay, so please continue that and see what you get for x. Leave values in, or leave the exponents in exact values, please. So I'll subtract 3x from both sides, so I get negative x equals 15, and then divide both sides by negative 1, so I get x equals negative 15. Okay, moving right along, we'll do the same sort of thing here for this next example. Let's get a common base. So please, by following the above example, please pause the video and continue this, and then play the video again after you're finished to check your solution. So this is already a common base of 5, and then I'll change 125 to 5 cubed to the x minus 3, and I guess brackets would be good. And then I'll just expand the powers here, so I get 5 to the x plus 1 equals 5 to the 3x minus 9. And then both sides are equal to each other, and the bases are the same. That means that the exponents have to be equal. So x plus 1 equals 3x minus 9. Collect the variables to one side and the constants to the other, so I'll subtract 3x from both sides. So I'll get negative 2x, and I will subtract 1 from both sides. Negative 2x equals negative 10, and then I'll divide both sides by negative 2, so x equals 5. Alright, let's take a look at the next example here. Do this in a couple different ways. So we want to solve 4 to the x plus 1 equals 64 to the 2x. So we could get a common base again and solve this, but let's use logarithms this time. So we've got 4 to the x plus 1 equals 64 to the 2x. And using common logarithms, that just means that we'll take the log of both sides. So take the log of 4 to the x plus 1 equals log to the 64 to the 2x. Now both of these have a log of, or base of 10, okay, because it's not written, so it's understood to be 10. And then using laws of logarithms, I will take the exponent for each of these and bring them down in front. So I'll get x plus 1 times the log of 4 equals 2x times the log of 64. Okay, and then we'll continue. So I'd like to get a common logarithm on both sides, so this x plus 1 times log of 4 will stay as it is, and log of 64, I'll change that to log of 4 cubed. Bring the 3 down in front, so I'll get x plus 1 log of 4 equals 6x log of 4. Okay, so we have common logs on both sides, so those will just disappear, so we're just left with x plus 1 equals 6x. 1 equals 5x because I subtract x from both sides. Then I'll divide both sides by 5, so x equals 1/5. Okay, so let's take a look at doing this another way, using base 4 logarithms. So again, 4 to the x plus 1 equals 64 to the 2x. And take the log of base 4 of both sides. I'll bring the exponents down in front, following the laws of logarithms. And then we'll get a common value here of 4 to match the log on the other side. And then again, now I'll bring the cube down in front. And that becomes 6x log of 4 to the base 4. And then we know that this just equals 1, this just equals 1, so those disappear, so we're left with x plus 1 equals 6x. Again, subtract x from both sides, and now I divide both sides by 5, so I get x equals 1/5. Okay, now let's take a look at this example. This one's could be a little more challenging. So we need to find the value of x, but we see that the bases are not the same. So especially in this case, it's important to then take the log of both sides. So we'll do that. Then I'll perform a couple laws of logarithms here. So I will change this to log of 2 plus the log of 5 to the x. And then I'll bring this x plus 1 down in front, this log of 10. Okay, by bringing the exponent down in front, and first I separated these two into 2 logs. And then what I'll do is I will bring the x down in front, so we've got log of 2 plus x log of 5 equals, and then I'll distribute this through, so I'll get x log of 10 plus log of 10. And then what I'll do is what will I do here? Let's subtract this from both sides, so I'll get log of 2. And this here, this log of 10, that actually just equals 1, so I'll subtract that from both sides, so I'll do that at the same time. Then I'll combine some more laws of logarithms again here, so I'll factor out the x. So I'll get x log of 10 minus log of 5, and that equals log of 2 minus 1. Then here I'll change this, so I'll get x log of 10 divided by 5, and that still equals log of 2 minus 1. Then I'll simplify this part, put this up over here. So log of 2 minus 1 equals x log of 2. Then I'll divide both sides by log of 2 because I want to isolate for x. So I get log of 2 minus 1 over log of 2 equals x. Now please be very careful here. Those log 2 of base 10 do not cancel each other out. Okay? Because we've got 2 terms up here and only 1 here. And so then just calculate that out, and x equals negative 2.32. Now if you were to check that, substitute negative 2.32 in for x here, work out the left side, and substitute that into 10 to the x plus 1 over here, and you'll see that those two sides will give you the same values.